Welcome back. This is Angie again. In order to fully understand decimal and percent concepts, we need to take a couple steps back into place value. Videos later in this module will look at different operations, but for now, this video is going to focus on place value development. As we go through this module, you'll be asked to pause and think at certain times, and at other times, there might be a task or a video that pops up. Take these moments to do the task, watch the videos, and reflect on your own. Your work will help with the assignments and reflection prompt for this module.
In this module, we're going to look at place value concepts and how to develop these with children. We'll have the opportunity to watch some student videos and experience tasks that help develop place value understanding. Take a moment to identify where you think 1,000 would fall. Go ahead, pause. Where do you think I would place 1,000 on this number line? Press play when you're ready. Where did you place 1,000? What strategy did you use? You may have used this strategy thinking, I divided 1,000,000 by 10 to find 100,000. Then I can divide 100,000 by 10 and locate 10,000. Next, I divided 10,000 by 10 to locate 1,000. You used your base 10 knowledge and equally divided a quantity by 10 each time to determine a smaller unit. Take a moment to look at these base 10 charts and think about what it shows and how it's potentially useful. Pause here if you need to take some time. Numbers in our system grow by increasing powers of 10 as you go to the left and decreasing by powers of 10 as you go to the right. At the center of this chart is our base unit of 1. We often see place value charts where the decimal is seen as the balance point of the number system. But shifting our focus to the ones place, our base unit, instead helps us see symmetry across the number system and can help answer the question of why aren't there ones? Which is a logical question if your focus is on the decimal point as the center. Instead, if we get to the unit of 1 and have to decrease by a power of 10, we end up dividing by 10 and thus having tenths. It's notable that in our normal number line, we increase to the right, yet in how we write numbers, we start with the largest place value to the left. Students come to us with these conflicting conventions about place value and number lines, which may result in some misconceptions. We don't want to get rid of this chart or number lines, but we simply want to have kids see this as not a number line, but rather a tool for a specific purpose. It helps us to understand the way we write numbers. Throughout elementary school, students are developing an understanding of our base 10 system that will support them in working with larger numbers and understanding concepts like decimals and scientific notation as they move into middle school. These concepts connect directly to the ideas of iterating and partitioning. As we move up in place value, we are multiplying by 10 or iterating the current place value 10 times, repeating it. This connects to the idea of powers of 10. So 100 can be thought of as 10 times 10, or 10 to the second power. 10,000 can be thought of as 10 times 10 times 10 times 10, or 10 to the fourth power. In thinking about the previous slide and the base 10 chart, our notational system combines the multiplicative relationship, 10 times the value of the unit to the right, with the positional system, where each place has a value. Let's focus on these first few place values. What we can notice is that we move from 1,000 to 100 to 10. We are dividing by 10 or partitioning each into 10 to find the next place value. And each time that power of 10 drops by 1, so 3, then 2, then 1. So moving to 10 to 1, we are likewise dividing by 10, and the power of 10 drops again by 1 to 0. Likewise, when we move from 1 to a tenth, we are partitioning by 10, and the power of 10 drops to -1. This could be an exploration of the mathematical practice 8. What is the pattern of growth, and why does it continue in a regular fashion? Young children have some knowledge of two-digit numbers. They can count up 2 digits and identify the names of digits, but place value development takes time. Students progress through different levels of understanding the concept of 10 and the idea of unitizing, which is composing units to make a new unit. In the first level, the initial concept of 10, a student does not see 10 as its own unit. There is no sense of grouping by a 10. 10 objects are 10 individual units of 1. For example, the number 34 means 34 ones, and the students don't separate the quantity into its place value groups. If you see a child counting a large quantity by ones, this is his level of understanding. In the next level, the intermediate concept of 10, a student begins to see 10 as a unit, but still relies on models to compute when working. To compute when working with units of 10. A student will count bars of 10 by saying 10, 20, 30, and so on. The idea that 10 ones make 110 is a really key shift in mathematical thinking and the beginning of the understanding of powers of 10. A student with a facile concept of 10 can easily count and compute by tens without models. Traditionally, teachers assumed students had a solid sense of place value understanding if they could identify the value of the digit, identify the names of the places, and expand a number with a standard notation. While these skills demonstrate some place value knowledge, they don't represent a deep conceptual understanding. Students can provide correct answers to these types of problems without a strong understanding of the base 10 number system. We're now going to do a series of tasks that press students' place value understanding at a deeper level. As we discussed when looking at the problem types, context provides students the opportunity to do mathematics and productively struggle. Given a context, students can act upon and represent quantities and relationships as they develop a solution strategy. Pause here and choose one of these two problems to solve without the use of a standard algorithm. In the next slide, you're going to see a video of Brennan. He's a 7-year-old student, solve the problem of 486 in 2 boxes of 10.
10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 2 times 10 and 4 times 10 would be 4 times 10 is 40. Now I have 60 more, so another 6. I have 46 right now. Then I get 8, and well, that makes it 47 because plus 1 more.
Take a minute to press pause and take a look at the solution methods for the first problem. Think about what productive struggle looks like. Are some of these going to be too easy? Do they show a level of understanding that the kids should have? So let's take a look at this problem. What does productive struggle look like? It needs to be challenging, but it also needs to be an accessible number set. And then we can scaffold with a visual. Pause here and read these problems. How are they related? How do they reinforce the concept of composing a 10? Press play when you're ready to resume. By using groups of 10 in each context, these different problems press students to work and reason with tens. You may have noticed that the building a system of tens and ones is a multiplication problem, and the packaging and filling is a division problem. The grouping problem considers the use of remainders and extras. By having the opportunity to struggle through these types of problems, children will experience composing groups of 10 and arrive at the idea that counting by tens is easier to do and more efficient than counting by ones. Children will begin with a count by one strategy and eventually develop a counting by 10 strategy. One way to help students shift thinking is to ask them, how can we count our objects in a way that it's easier than counting by ones? Sometimes students will still need to count by ones to convince themselves that the quantity is correct. as they are still cognitively constructing this concept of 10. You're going to watch a video for each of these 3 problems. Before you move on and watch, pause and take a look at these problems, kind of work through them yourself and get an idea of how you might solve them, say if you don't have an algorithm. As you watch the students, think about how the solution strategy reveals the understanding of the base 10 system. Also refer back previously if you'd like and think about where each child is developmentally. Does the child show an initial, intermediate, or facile concept of 10?
So do you remember about those over there, those cubes that are all stuck together? How many are in each one of those stacks? You can grab one and count it if you need to. Okay, there's 10 in each stack. And we actually made them all the same, so they're all 10 in each stack. Okay? So you can use those any way you want. It might be helpful. All right, so Mrs. Rojo is getting ready for the school year and wants to figure out how many markers she has. She's got 10 markers in each box, and she has 3 boxes of markers and 4 extra markers. So what I want to know is how many markers does she have?
$34.
34. Nice work.
Ms. Rojo wants to figure out how many markers she has. She has, markers come, there are 10 markers in a box. Okay, so Ms. Rojo wants to figure out how many markers she has. There are 10 markers in a box. She has 3 boxes of markers and 4 extra markers. How many markers does she have?
$34.
How did you get that?
Because if you have 30 and then you add 4, that equals 34.
I got it. Thank you.
Ms. Adams has 85 markers. If 10 markers fit in a box, how many boxes can Ms. Adams fill?
$8.
How'd you get 8?
Because there's 10 in each one, and then there's in 80 there's 8 tens.
How did you know that in 80 there are 8 tens?
Because there's 10, 20, 30, 40, 50, 60, 70, 80.
Did you do that when you were solving the problem? Did you count by tens like that, or did you do something else?
I counted by 10.
Okay.
Ms. Green has 321 markers. If 10 markers fit in a box, how many boxes can Ms. Green fill?
Do you mean how many boxes can she fill if she uses all the markers? Or how many boxes can she get to be full?
The second.
32?
How'd you get 32?
100 divided by 10 is 10. So 300 divided by 10 is 30. And then 20 divided by 10 is 2. And then 30 plus 2.
Oh, okay.
As you see in the videos, the students are able to solve the problems, yet the strategy each child uses is a window into their understanding. For example, the first student uses the bars of 10, but is not able to count each bar as 10. Once grouped, she goes back to count each cube to get 34. The fourth student demonstrates a strong sense of place value. Not only does she use mental math to solve the problem, but she articulates well the idea of 10 tens in 100 and 30 tens in 300. Imagine this student's ability to work with decimals and scientific notation later in grades. Giving students tasks using models is another way to develop place value ideas. Models are powerful tools that allow students to physically manipulate and visualize the base 10 concept, thus deepening their understanding. They can construct and see 10 as both a single unit or as 10 units of 1. They can see 100 as a single unit or as 10 units of 10, or even 100 units of 1. Asking students to show multiple ways to represent a number can reinforce these relationships between ones, tens, and hundreds. Groupable models such as cubes, counters, popsicle sticks, straws, and beans are easy to group into units of 10. It's important to use models students can group before moving to pre-grouped models such as base 10 blocks. Take a moment to find 5 ways to represent 125. A student's ability to decompose a number in a non-standard way demonstrates a strong understanding of place value and equivalent relationships. The student understands that each digit represents a unit, but it can be partitioned into many different units and still be equal. For example, 125 is the same as 9 units of 10 and 35 units of 1. Think about how this is connected to flexible computation strategies, something we will continue to discuss in the next module. We can also use the bar module to make connections between notation and units of 10 and 1. Pause here and consider these questions. Pressing students to show how the model represents the digits in a numeral emphasizes the idea that the 3 is 3 units of 10 in 32 and 3 units of 1 in 23. Though both numbers use the same digits, the places of the digits signify different units as seen in the bar model. In elementary grades, we often use a 100 grid to develop concepts of place value. But as students move up into larger place values, we can make a 100 grid of 100 grids to we can make a 100 grid of 100 grids to visualize larger numbers. Take a moment to answer these questions by looking at the grid in your Pause and Play book, and then review the answers. What's nice about this visual is that it goes all the way up to the 10,000 place, allowing us to visualize about powers of 10. That first question really presses us to multiply by 10 repeatedly, seeing the growth to the powers of 10. Questions like this one ask us to relate fractions to large numbers, stressing mental math, but the visual also serves to visually reinforce. If each row is 1,000, then 2 rows, or 1/5 of the grid, would be 2,000. We can take that away from 1 to find 4/5, or iterate that 2,000 4 times. Either way, we get 8,000. In developing these key ideas about place value, students are expected to make connections across many skills and concepts. We want to keep in mind the questions we pose to children, the activities we provide, and the language we use to describe these connections. Students must make meaning of the 10 makes one relationship. So let me repeat that. Students must make meaning of the 10 makes one relationship. We can do this by asking students to connect their strategies to models and by calling attention to groups and their oral and written names. For example, given a grouping of 2 10s and 12 ones, and a grouping of 3 10s and 2 ones, what questions could you ask students? Are they equal? How do you know? How are the units in each grouping the same or different? How can we count these quantities? What number names do we use to represent each grouping? What numerals do we use to represent each groupings? By working through these types of questions, students comprehend how digits, positional number names, and units give meaning to each other. As students become more confident about place value, we can start to ask questions that press them to think beyond the value of a specific digit and start to see relationships between the place values. Place value riddles do just that. For example, we might ask how many tens are in a number, pressing beyond just 5 or 4 to think about how many full tens are represented within the whole number, similar to the candy problem. Take a moment here to solve these problems and then move on to the next. Depending on the age level, students might answer this problem in one of 2 different ways. Initially, we may just be thinking about full tens, 5 full tens, 24 full tens, or 103 full tens. But eventually, we'd want students to think about the unit as 1/10 of a 10. So we can think about 3 as 3/10 of 10, making this answer 5 and 3/10 rather than just 5. The other riddles press students to make new units to find the total. Reflect back and compare these to the traditional place value questions presented earlier in the module. Learner-generated examples are a great way to differentiate an activity and really look for student understanding. Try these problems, but as you work, think about how a student who is really comfortable with these concepts might approach these problems, as opposed to a student who is just beginning to grasp the concept. Learner-generated examples are a great way to differentiate an activity and really look for student understanding. Students will often say when doing this string that the 0 from the first line just moved to the other number on the left side of the equation. Push them to notice that really each number either increased or decreased by a power of 10. As students figure out the power of multiplying by tens, they often say just add a 0. I mentioned this in an earlier video. 12 times 10 is 12 plus a 0. Well, 12 plus a 0 is 12, not 120. Using precise language is a part of our math practices, so push them to notice that really the number increased by a power of 10. The number's place value increased by 10. This understanding is critical as students move to working with decimals. A common misconception in later years is to see a student compute 1.2 times 10 as 1.20. Adding a 0 always worked with whole numbers before, but this faulty reasoning breaks down when operating with decimals. Quick Writes press students to reflect on major concepts or how particular problems are similar or different. We've worked with a number of teachers who have started asking students to categorize problems or compare two problems on homework or classwork in order to increase student focus on certain concepts. In this example, we're asking you as teachers to reflect on these 2 strings. Take a minute and examine each string and consider what is similar about the concepts the string explore and what is different. String 1 is encouraging students to use mental math to figure out percentages based on what they know. For example, we can have 100 of 72 to find 50% of 72, and that's 36. We can then divide 50% by 5, or 100% 10, to find the value of 10% as 7 and 2/10. Doubling that value would give us 20%. We can find 5% by halving the 10%, or dividing 50% by 10. Then we can compose the 10% and the 5% to get 15%, is 10.8. We've just used base 10 understanding and doubling and halving to find a bunch of different percents without needing a calculator or pencil paper. Stream 2 develops the idea of making use of mathematical structure, seeing how we can take advantage of known relationships and patterns. This string leads to the surprising realization that 25% of 16 is the same thing as 16% of 25. Let's take a moment to examine why. Visually, if we take 16 as the whole, 100%, we can find 50% by halving it to get 8. To find 25% by halving again to get 24. If we make 100 the whole of 100%, 16% would just be 16. If we change the whole to 50 but still take 16%, we can just have what we found when the whole was 16 to get 8. We can then find 16% of 25. We can take the half of what we found when the whole was 50 to get 4. Another way to think about why 25% of 16 is the same as 16% of 25 is by using the properties of multiplication. 16% of 25 is the same as 1/100th of 16 times 25. Using the associative and commutative properties of multiplication, we can rearrange that expression to be 1/100th of 25 times 16, which is the same as 25% of 16. Both explorations use the structure of the mathematics to simplify calculations and regulate something that students may struggle with procedurally, the algorithm, to something they can visualize and calculate with relative ease. A return to number sense, operational thinking, and generalization. Create the fraction in each of the 100 grids. Use the previous picture to create the decimal notation for the area filled. Here are just a few examples of something that you could have created. So let's take a look at just assessing place value. And I just want to give you some caution. While students could fill in missing numbers correctly when asked to count to 100, some students are confused when changing from one decade to the next. For example, stumbling when they reach 29, not sure what came next. When asking students to write a number like 38, some incorrectly would write 308, writing 30 and 8. While they could tell which digit was in the tens place and which was in the ones place when comparing 54 and 45, for example, some could only offer the explanation of that 54 is greater because it comes after 45. Their explanations didn't relate to their place value of the digits. By the end of first grade, students are expected to understand that 2 digits of a 2-digit number represent the amount of tens and ones. In second grade, they extend their understanding to 3-digit numbers and the meaning of the digits in the ones, tens, and hundreds. First and second graders are generally familiar with numbers up to 100. Many can write the numbers. Many can compare numbers, for example, 54 and 45, and tell which is greater. Many can identify which digit in 2-digit numbers is the tens place and which is the ones place. I think we have all seen these types of assessments to check students' understanding of place value. Here we see a worksheet where students fill in missing numbers, circle the greater numbers, and indicated whether digits were in the tens or in the ones place. But if we pause to ask student questions face to face, sometimes their responses are surprising and give us disturbing evidence of really shaky understanding. Rather than a paper pencil assessment, let's consider a student interview. We want the interview to be short because the information is important to have for all students in the class. Efficient, requiring a minimum of materials, and informative, giving clear information about student understanding. We're going to watch a video of Anna, Daryl, and Jonathan as they're interviewed for some place value understandings.
Can you write the number 16 kind of big here? Yep, that's 16. And I'm going to show you with the cubes what the 6 means. Here are 1, 2, 3, 6 cubes. Can you show me with the cubes what the 1 in the 16 means?
What?
Can you show me, I showed you with the cubes what the 6 means in the number 16. Can you show me with the cubes what the 1 means in the number 16?
It means 10.
Can you write the number 16 right here, kind of large? Okay, that's the number 16. And I will show you with the cubes what the 6 means. 1, 2, 3, 4. This is what the 6 means. Can you show me with the cubes what the 1 in the 16 means?
Ten.
Would you write the number 16 right underneath the cubes, kind of big?
Okay. Sure.
Thank you. And if I showed you with the cubes what the 6 means, I would do this. I would say, here are 6 cubes, and that's what the 6 means in the number 16. Could you show me with the cubes what the 1 means in the number 16?
That's 10.
So show me with the cubes.
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I guess you scoot it over.
I would.
In Anna's video, after asking for the question to be repeated, Anna responds automatically that the 1 in the number 16 means 10. In Daryl's video, Daryl says correctly, counting out the remaining cubes to show that the 1 in the number means 10. In Jonathan's video, Jonathan also demonstrated his understanding of the meaning of digits. However, the other students' responses indicated their lack of understanding. Let's watch Gabriella for a minute. You might want to try this assessment with your students. Maybe first predict what individual students will say and do, then ask and see what you learn.
Couldn't you write the number 16? Kind of big. Okay, and you wrote the number 16, and I'm going to tell you with the 16, I see the 6, and I can show the 6 with the cubes. I can show 1, 2, 3, 4, 5, 6, and that's what the 6 means in the 16. Can you use the cubes to show me what the 1 means? Okay, and what about these cubes?
I guess they wouldn't be. I guess they wouldn't go there.
Okay.
Let's take a moment to connect to the standards for mathematical practices. Think about how the information that we've presented and talked about in this section relate to the math practices. If you had to pick 2 that stood out to you as a focus, which ones would you pick and why? Jot down your thoughts. So in this module, we looked at place value understanding as well as tasks to better develop place value. So hopefully you were able to pick up some good tools and strategies to help improve your instruction.